Okay, so we're going to wrap up our discussion of thermodynamics by talking about Gibbs free energy that is calculated under non-standard condition. And to explain this idea, I want you to consider the following situation. Here's a really simple reaction, which is just the evaporation of water. So water liquid going to water gas. If we look at our thermodynamic values and calculate the delta G, so just taking liquid to gas here at 25 Celsius, which we can do by calculating the delta H and delta S and then using that formula delta G equals delta H minus T delta S, we find that the delta G standard that we calculate would have a value of positive 8.590 kilojoules. Okay, so these are calculations we've done in other sections before, so hopefully you're able to get this yourself. Because it's a positive delta G, that tells us that the reaction is not spontaneous, which tells me that if I were to have water at 25 Celsius, that water is not going to evaporate, okay? However, this goes against the actual experimental observation. If I were to spill water on a floor at room temperature, eventually all that water will evaporate, even though the temperature of that room could be maintained at 25 Celsius. So clearly, this calculation is not really representing reality. So there must be something about the number we calculate that is not quite right. And in fact, what we calculated here is delta G standard, which is delta G where that experiment is carried out under standard condition. And what you have to remember about standard condition is that pressure has to be maintained at 1 atm, something that you should remember back from Gen Chem 1. So that's what we refer to as standard conditions. This is a special set of conditions where we measure thermodynamic values so everybody can use those numbers in their calculation. What we're saying here is that the number we calculated where we get positive 8.59 is really a condition where the pressure of water gas is 1 atm in the air around it. But if you look at a table of vapor pressure of water, which is shown here on the right, and room temperature, which is about 25 degrees Celsius, you see that the vapor pressure of water is pretty low. It's 23.756 torr, which if you convert it to ATM is actually going to be a pretty small number. And so we're really far away from that standard condition pressure of 1 ATM. The number we get, therefore, is not really useful because we're not at standard condition. So the question then becomes, how do we calculate delta G when we're not at standard condition? Can we do it? And the answer is yes, we can, but we have to come up with a equation that would specifically allow us to calculate delta G under non-standard conditions. To do that, I'm going to bring back a concept that we learned early on about equilibrium, which is that we can predict the direction of a reaction by comparing Q to K. Q is our reaction quotient, which is basically just the same ratio as what we have in our K expression, except that we're calculating Q at some non-equilibrium concentration. Could be any time during the reaction when we're not at equilibrium, okay? And when we compare Q to K, it tells us which way the reaction is going. We can connect this with delta G that is calculated at non-standard condition, which I just give the symbol delta G, so without the degree symbol. Delta G also tells us the direction of a reaction. When we get delta G negative, we know that the reaction is spontaneous in the forward direction, right? It's going towards the product. So we can put both of the quantities together and try to relate them in an equation. Specifically, if we have a reaction A goes to B, spontaneous means it's going to go towards B on its own. We know that the Q should be less than K when we calculate it. If Q is less than K, that means Q over K should be less than 1. We also know that reaction is spontaneous when delta G is negative. So that's one fact. The other fact is when the reaction is not spontaneous, which means that it's going this way, we know that that Q is going to be bigger than K. Again, another way of saying that is Q over K is greater than 1. But another way to think about that is delta G has to be positive for that reaction. And lastly, we know that at equilibrium, Q is equal to K, or Q over K is 1, and delta G is equal to 0. Well, the equation that would make sense that we can write is this equation right here, which is delta G is equal to RT ln Q over K. The reason this works is because if you look at that RT ln Q over K expression, it should fit all the three scenarios that we just had. If the reaction is spontaneous, Q over K is less than 1. That means the overall delta G is going to be negative, because if this is a fraction that's less than 1, then ln of that fraction is a negative number, and so we get our delta to be negative. If our q over k is bigger than 1, that means our whole delta g expression is going to be positive. Delta g positive is spontaneous, so again, that match our description of q and k comparison. And then lastly, if q and k are the same, which means that q over k is 1, ln of q over k is 0, so delta g should also be 0, and that's exactly what we see here. Everything matches, so that means that this is how delta G relates Q and K. Now, a lot of time, this equation is also written this way, which is just the more expanded form of the ln once you split it into ln of Q and ln of K. The reason why it's written that way is because when you see it that way, you can see that what delta G is measuring is basically the difference in energy between a reaction not at equilibrium and a reaction at equilibrium. So another way to say that is delta G is measuring how far is a reaction from equilibrium, right? The difference between the two positions, one equilibrium and one not equilibrium. The one that is current concentration is expressed by your Q measurement, and the one at equilibrium is expressed by your K value. Now, the free energy itself is going to be large if you're pretty far away from equilibrium. But if you're pretty close to equilibrium, then there's not a whole lot that you're going to get in terms of free energy, okay? So that's what delta G is actually measuring. It's really, when we say delta G, it's really a measure of a difference in chemical potential energy of a reaction compared to its equilibrium concentration of the reactants and product, okay? So therefore, just to wrap this up, right, when we want to determine spontaneity, we shouldn't calculate delta G standard, which is this one. What we should calculate is delta G, which is just that symbol, which is the delta G under non-standard condition. Delta G standard is really only useful for calculating spontaneity for reactions that are carried out under standard condition, which is a pretty limited set of conditions. Most of the time when we run reactions, we are not at standard condition. Now, the standard free energy, though, has a lot of use. That's the reason why we have that table, which allows us to calculate the standard free energy. One of the usefulness of the standard free energy is how it relates to the equilibrium constant. And we can look at it this way. First off, just a reminder, as I mentioned earlier, when we're talking about standard condition, we're talking about a pressure of a gas that has to be at 1 atmosphere and a concentration of a solution that has to be at 1 mole. These numbers are useful for us because if you look at that relationship between delta G and Q and K, which is delta G equals RT ln Q over K, if my reaction is under standard condition, that means my Q automatically is going to be 1. How do I get that? Well, if you calculate in Q, which is just ratio of concentration, but then all the concentration required to be 1 to any power is always 1, so your Q is automatically going to be 1. If you're calculating QP for pressure, all the pressures are required to be 1, so 1 to any power is also 1. So in other words, your Q is going to be 1 at standard condition. So if your Q is 1 at standard condition, that means the expression simplifies to the following, right? Which is delta G standard, now, because we're talking about specifically standard condition, should equal RT ln 1 over K. ln 1 over K is the same as negative ln K, so then we can write our delta G standard as just negative RT ln of K. This is a really useful equation because now we can connect the value of delta G standard to the equilibrium constant. So all of the equilibrium constants we learned so far in this semester, from those generic equilibrium constant all the way to Ka, Kb, Ksp, and the formation constant for the complex ion, can now be used to calculate the delta G of all of those specific reactions for acid, for base, for the solubility equilibrium, and so on. So let's take a look really quickly at an example of how to do this. This example just says, find the K for the reaction NO plus half O2 goes to NO2. Delta G standard equals negative RT ln K. So equilibrium constant must then be equal to E to the power of negative delta G standard over RT. Now, the reaction that's given is this reaction right here. So in order to get our K, I'm going to need to get my delta G standard. I could get that using my thermodynamic table. I've already attached a piece of it here. You can look it up also on your own through the link that was provided in prior videos and in your lecture notes. But I'm showing only the NO and the NO2 here because remember that O2, which is another species in the reaction, is oxygen standard state. And any species in the standard state, its delta G of formation is equal to 0, right? So if you were to go ahead and calculate it using your delta G of formation formula, you're going to get delta G standard equal to negative 35.24 kilojoules. Tells you that the reaction is spontaneous. We're going to expect our K to be a larger than one number, okay? So let's go ahead and calculate our K. K is e to the power of negative delta G. Don't forget that negative in front. The delta G itself is negative also, so it's a negative negative. And then the R value should be your 8.314 joules per Kelvin. The temperature we're asked to calculate is 298, so we end up getting 1.5 times 10 to the 6, which is a large K value, so we know this reaction product favor, okay? The K and delta G standard relationship is exponential, so that small change in the delta G value is going to give a pretty large change in the value of the K. So you can see here how just changing, for example, from 200 to 100, you get a pretty sizable change in the magnitude of the K, right? The last equation I want to present to you here is just the equation for the non-standard delta G. Remember that we already had it earlier. It was written as delta G equals to RT ln Q minus RT ln K, but I'm going to write it now as negative RT ln K first plus RT ln Q. And the reason is because that negative RT ln K we just show is equal to delta G standard. So now we can write it as just delta G standard plus RT ln Q. And so this part that's highlighted in yellow is equation that would allow us to calculate our delta G at non-standard condition. So basically you have to calculate your delta G at standard condition, and then afterwards you have to add this second factor, which corresponds to how far that number is from the equilibrium position. Okay, so let's take a look at the reaction that we were looking at, which is that water that's being spilled on the floor, right? At 298 Kelvin or 25 Celsius, that water will eventually evaporate. So it's telling me that that process of liquid going to gas water is spontaneous. So let's take a look if we get a negative number when we calculate our delta G. We had the delta G standard earlier, but we have to get at this new component, which is RT ln Q. And the Q here we can calculate because the reaction is just liquid going to gas. The Q is just the pressure of the gaseous water at that temperature. And again, earlier I was using this number, so I'm going to use that number as my pressure of water. When you end up calculating the value, you get a negative number. It's a small negative number, but that still tells you that the reaction is spontaneous, okay? That when water is spilled at 25 Celsius, we see that the water evaporates spontaneously. All right, let's take a look at an example on how to use some of these equations. We have a reaction here, which is SO2 being combusted to produce SO3, and we want to calculate the K at 298 Kelvin. And then if we have some combination of SO2, O2, and SO3, right, will the reaction be spontaneous? Will it proceed towards the product side? And then lastly, calculate the delta G for that reaction that was given in B. Start with the reaction written right here. 2SO2 plus O2 goes to 2SO3. You can calculate the delta G standard by finding delta G formation values in your thermodynamic table. I just wrote out the exact equation you have to use here, but the numbers you're going to need to find yourself. The delta G standard end up being negative 141.732 kilojoules. K is e to the negative delta G standard over RT. When I plug in the numbers, I end up getting about 7 times 10 to the 24th. So definitely a very product-favored reaction. We see that both in the value of the delta G standard as well as the value of the K. In number 2, we were given some concentration of each of these 3 gases, and we were asked, will the reaction proceed to equilibrium? It's another way of asking, will the reaction be spontaneous or not? There are 2 ways to solve this. You can either just compare the Q to K. That would be like sort of the method we had learned in prior section, or we can calculate the delta G under non-standard condition. What I want to do is use method 2 here, which is to calculate delta. Remember that delta G is equal to delta G standard plus RT ln Q. We already found the delta G standard is negative 141 kilojoule, but now we need to just calculate the RT ln Q component of it. So the R is this, the T is this. ln Q, remember that our reaction is 2SO2 plus O2 goes to 2SO3. So the Q expression is going to be SO3 squared over SO2 squared times O2, okay? And so that's what I have here. And the numbers I put in there is just the numbers that was given in the question. That ends up giving a delta G equal to negative 138. So the delta G, again, not delta G standard, but delta G is negative 138, which tells me that the reaction is spontaneous, okay? And so if you look at the last question, it actually asked me to calculate delta G for the system, and I already did that. I just found that value to be negative 138. Whether the reaction is carried out under standard condition or under this new condition that they gave us, the reaction is still going to be spontaneous.